This lesson is about exponential functions in the real world. Exponential growth, exponential decay. Look, a lot of things in life grow exponentially. For example, population. If you looked at the growth of population over time, we would expect population to increase more and more rapidly. That would be exponential growth. Also, savings. You would hope that if you put your money into some sort of an interest-bearing account, that the value of your savings would increase more and more rapidly over time. So your money, your savings would grow exponentially over the years. So when things are increasing more and more quickly, that is exponential growth. That happens a lot. But there's also exponential decay. A good example of exponential decay would be the value of a car. When you first buy a brand new car, when you drive it off the lot, maybe that car is worth $30,000, $40,000, whatever that car is. But your car is never more valuable in the majority of cases than that first day. As soon as you drive it off the lot, the value of your car begins to drop. And over the years, the value of your car gets less and less and less and less until eventually it's really not worth anything at all. So that would be an example of exponential decay. And there are many things that work like car value where they decrease. Unfortunately, the endangered species, when the populations are declining, they can decline exponentially over the years. All right, so we have exponential growth and exponential decay. Each of those have their own formula that's very simple and similar. For exponential growth, this would be the formula for exponential growth. Okay, we're looking at this formula. The b value is the beginning amount, whatever it is. And then we're going to do 1 plus the rate to the power of time. And we'll see exactly how that works in a moment. But the only difference between the exponential growth formula and the exponential decay formula is for exponential decay, we're doing 1 minus the rate instead of 1 plus the rate. Okay, let's look at some problems. Okay. A new flat screen television costs $1,200. The value of the TV decreases by 21% each year. Write an exponential decay model giving the TV's value after X years. All right, so we're talking about exponential decay. So we should be looking at the model that works like this. That has this basic form where B is the beginning amount. Because this decay, we're going to do 1 minus the rate to the power of time. Now, I'm going to use other variables. Since we're talking about the value of a TV, then I'm going to use V. Okay, this B is the beginning amount. The beginning value here is $1,200, $1,200. So that goes here. Next, we have 1 minus the rate. Okay, now this rate is the 21%, but R has to be written as a decimal. So if I want to convert 21% to a decimal, all I do is I take the invisible decimal that's at the end right here, and I move it twice to the left. You know, basically I'm dividing by 100. So that's why this R, the rate is going to be 0.21. Okay, and that's the decay rate. So that's why we'll put 0.21 right here. Okay, and then to the power of time. It says after x years, so I'll just put x here because that's the variable that they mentioned in the problem. So this would really be the model. You should go ahead and do this subtraction though to get yourself a nice decay factor. This the number in the parentheses is known as the decay factor. So if you do 1 minus 0.21, and you should be able to do this in your head. Okay, I typed it in wrong. 1 minus 0.21. Okay, that is 0.79. You know, think 79%. But 0.79 is going to be your decay factor. So the model would be written like this: 1,200 times 0.79 to the x power. Okay, so this is the model. This is how you should write it. Okay, so notice, just practicing our vocabulary, the decay factor is 0.79, and this is the decay rate. Whoops. Okay, the decay rate is 0.21. All right, so be familiar with those two terms. Okay, this percent turned into a decimal, that's the rate. And once you add or subtract from 1, depending on if it's growth or decay, and you get this number in the parentheses here, the base, that is the decay factor or the growth factor. Okay, anyway, use this model to estimate the value after 3 years. All right, well, x represents the number of years. So the value after 3 years will be 1,200 times 0.79 to the third power. So we can just put that in the calculator. Okay, 1,200 times 0.79 to the third power. Okay, 3 years. Okay, so we started off with a value of $1,200, but after 3 years, it's approximately has a value of $591.65. All right, there's not a lot of need to be that precise, but for now, let's just keep all those pennies. So what did I say? $591.65. Okay, that's how you do that. All right, let's take a look at the next one. You buy a new computer and accessories for $1,500. The value of the computer decreases by 16% each year. Write an exponential decay model giving the computer's value after t years. Okay, so this is almost the same thing. So the value is going to equal the initial value, and then we have to do 1 minus the rate, okay? So we take the 16%, if we convert that to a decimal, the rate is 0.16. Okay, so we have to do 1 minus 0.16. And it says t years, so let's go ahead and use t this time. So this is basically the model, but let's go ahead and do this subtraction. So this should equal 1,500, okay, and this is going to be 0.84 to the t power, because 1 minus 0.16 is 0.84. Okay, so this is the model that would represent this situation. Now, use this decay model to estimate the value after 5 years. Again, that just means I'll let t be 5. So I will do 1,500 times 0.84 to the 5th power. And the calculator will help us out with this. What happened? So this should tell us the value after 5 years. And it's down to about $627.32. Okay, so those are examples of exponential decay. Now, when will the computer have no value? Okay, let's look back. Well, look, the short answer is the computer will never have no value. All right, this is kind of a silly question. Yeah, there will never be a time that the computer will have no value at all. Exponential decay involves getting closer and closer and closer to 0, but you never get there. The word for this is asymptote. Okay, the x-axis here, the 0, is an asymptote. So in this particular case, every year the value is 84% of what it was. But it's always going to be 84% of something. It's never going to be 0. Okay, so kind of a trick question because the real answer is never. But let me go ahead and mention this. You can use your calculator to see what happens to these values over time and sort of play around with it. Let's use the table function and put this function in and see what's happening. Okay, so go to your calculator, hit the table function, and we can just type this in. So 1,500. All right, decay factor. Use your caret to make this an exponent, and we'll say the x power. Okay, and we'll just start from 0. Just hit enter a few times. Okay, so year 0 represents right here at the beginning the initial value, the beginning value of $1,500. So this table is reflecting the value of this, what are we talking about? A TV? What are we talking about? Computer and accessories. Okay, so this table is reflecting the value of the computer after each year. So there's the value after 1 year, a couple years, or all right, we're already down to a little over $1,000, but you could keep going. Okay, and you can see it's getting less and less. All right, it's down to $312. Okay, after 11 years, 12 years, 13 years. Okay, now eventually the calculator is going to round this to 0. But, you know, so we're down to 23 years, we're down to $27. Okay, so if you keep going and going and going, all right, is that as far as my calculator is willing to take? No, we're still good. Okay, 34 years. All right, the computer's down to less than $1. I mean, less than $2. All right, now we're down to less than $1. All right, years go by. Theoretically, the computer's worth 29 cents. Okay, so really, eventually the calculator is going to round this to 0. All right, we're down to 7 cents now, but this is a little silly because the reality is the computer's always going to be worth something, so it's kind of almost arbitrary, like, okay, right around 70 years or so, this is going to start to round, we're down to a penny after about 70 years. Okay, yeah, it's just a matter of where you want to call it worth nothing. That is not a very good question, but I hope you see how you can use your calculator to play with the values and really see what's happening over time. Okay, so where do you want to call it? 68 years, 69 years, when is it worth nothing? It's still worth fractions of a penny. It's an open question. Anyway, moving on. Looking at number 3. Between these years, the population of Florida increased by 2.13% each year. All right, in 2000, the population was this. Write a model giving the population P of Florida T years after 1990. Okay, well, we're talking about increasing, so that's exponential growth. So I'm going to use P for population. All right, and first we write down the initial amount. So the initial population is this 15,982,378. All right, and then we do, because it's growth, it's going to be 1 plus the rate. Now, this percent growth, if I want to convert this to the growth rate, I need to change this to a decimal. And remember, I do that by, I take this 2.13 and I have to move this decimal 2 times to the left. So that's going to be like this, 1, 2. If I do that, then what I have is the decimal winds up here, and there will be this 0 in the front. Okay, so this rate is going to be 0.0213. Please do not leave off these decimal numbers. You're going to have to keep them. So we got 1 plus 0.0213, to the power of time. But of course, doing 1 plus 0.0213 is just the same thing as 1.0213. Okay, so that's the model. For some reason, a lot of times, even though you're being asked for a model, which means just an equation, students will try to put a number here for the t. Do not put any numbers up here. If you're being asked for a model, there should be just a variable, t or x, depending on the situation, in this case t. Okay? Then you can use your model to do stuff. So if I want to estimate the population in 2010, okay, since 2000 is where this initial amount came from, then 2010 is 10 years later. In other words, t is equal to 10. It's 10 years after the initial amount. So basically, you can get the population in 2010 by doing your 15,982,378 times 1.0213 to the 10th power. So just type all this in your calculator, and that will give you the estimated population in 2010. So that turns out to be about 20,082,707. I'm going to head and round it to the nearest person. Okay, let's see what else we have in this lesson. A couple more examples. All right, looking at number 4, an all-terrain vehicle costs $800. The value of the vehicle decreases by 10% each year. Write a decay model. So, the value should equal the initial value times 1 minus that rate. All right, 10%. That translates into a decay rate of 0.1. Okay, again, I took that 10% and I saw the invisible decimal point was right here, and I have to move 2 times to the left. So that's where I'm getting 0.1 from. So it's going to be 1 minus 0.1 in that case. Okay, to the power of time, okay, t years. So go ahead and do the 1 minus 0.1, all right, which of course should be 0.9. All right, if you 1 minus 0.1 is 0.9. So this is going to become, the value model will be 800 times 0.9 to the t power. So this is how you should go ahead and write your value model. Do not put any numbers here for t. Let it be a variable. Estimate the value after 5 years. All right, that would be the same thing as doing 800 times 0.9 to the 5th power. So we can use the calculator for this. Now I'm looking ahead a little bit. It says, when will the ATV be worth $500? To answer questions like this about when, we really are going to use the table function on the calculator. So I might as well, as long as I'm going to be typing in the model anyway, I'm going to use the table to answer both of these questions. So let's do that. So hit the table button on your calculator, clear out anything in there, and type in your model. So we have 800 times 0.9, to the x power. We don't have a t, we'll just use x. Hit enter. Go ahead and just start at 0 for now, just so we can see what's going on. So sure enough, the year 0 means the very beginning, and we're starting off with a value of $800. Okay, now as time goes on, we want to know the value after 5 years. So this is the value after 1 year, 2 years. We can just scroll down, 3 years, 4 years, 5 years. So after 5 years, the value is down to $472.39. Oh, well, that's supposed to be here. Okay. So the value is going to be, I already forgot what I said. 472. And 39 cents. Okay, so that's the estimate for that. Now, when will the ATV be worth $500? Okay, man, with these questions, we should be looking right here and looking for when it hits $500. But $500 is somewhere between 4 years and 5 years. So, it's almost, because this value is almost $500, it's almost the same answer, it's almost 5 years. So I'm just going to say between 4 years and 5 years. Between 4 and 5 years. Okay, last problem. Oh, not the last problem. Okay, there's a couple more problems. All right, let me accelerate. This video is getting long. A rare coin cost you $70. the value of the coin appreciates, all right? That means increases 2% each year. 2%. The growth rate then is 0.02 if I move that decimal point twice. So the model, okay, the value of this coin, it starts off as $70, but then we're doing 1 plus 0.02 to the power of time. Of course, 1 plus 0.02 is just 1.02. So you can just go ahead and put 1.02. So this is the model. How much will the coin be worth in 20 years? Okay, well, in 20 years, we will just use our model, all right, and put a 20 up there. So let's check that out. Okay, so it'll be worth $104.02. I'm rounding up. Okay, if you sell the coin, how much profit will you make? Well, if we sell the coin, all right, we're selling it for $104.02 minus the original cost to you, which was $70. And so that's going to leave $34.02 profit. Okay, now last problem. You buy a football signed by a football legend. It is valued at $500. It will appreciate, meaning increase, at a rate of 3% each year. Okay, 3%, that is a growth rate of 0.03. So the value of this football is going to be the original $500, and then here comes the growth factor. It's 1 plus 0.03, which is just 1.03 to the power of time. So that is your model. How much will the football be worth in 30 years? So you just do 500 times 1.03 to the 30 power. Just put that in your calculator and see what it is. What did it say? 30 years? So in 30 years, this football will be worth $1,213.63. Okay, all right, that's the end of this lesson. I hope that it was helpful to you, and I will see you on the next video.